So, I told you it is possible for me to introduce quantum mechanics starting with this particular approach, which thinks of the wave function as being obtained as a sum over all possible paths, right. You say that okay, if my particle is there and if I want to calculate the wave function for the particle at this location, at that location after a time 10 nanoseconds, then I have to think of all possible paths, not just one path, all possible paths. Each path I have to calculate its contribution, then sum up all the contributions, I will get the wave function, right. So, this approach was introduced by Feynman and it is referred to as the path integral approach. So, the approach is actually due to Feynman. Interestingly, this was his PhD thesis, this particular approach. You see, quantum mechanics was developed as you know in 1925-26, around that time. There were two avenues of attack. One was due to Schrodinger. Schrodinger was an expert on waves and he wrote down the wave equation which we are going to see. And there was also Heisenberg, he wrote what is referred to as matrix mechanics, he developed matrix mechanics. And then within an year or so, Schrodinger showed that these two mechanics which appeared to be very different, they were equivalent to one another. That was proved by Schrodinger a little bit later, within an year. So, therefore, there were two approaches to quantum mechanics, which one is referred to as wave mechanics, the other was referred to as matrix mechanics, and then the two together were referred to as quantum mechanics. But this approach that I have spoken about just now was introduced by Feynman in his PhD thesis around 1943 or so. And if you look into any chemistry book, you will not find this description, and as I said, this is the most physical, the nicest approach that one can think of. In fact, when I studied quantum mechanics, I studied it the traditional way. Traditional way means you introduce a Schrodinger equation as a postulate and then go on to develop everything from there, but I never had thought that I had understood quantum mechanics until I came across this approach, which made it as physical as possible. So, this is very strongly recommended, but unfortunately, as I was telling you in the previous lectures, mathematically speaking, it is a little bit difficult to handle, and therefore, what we are going to do is we are not going to adopt this approach, which is very nice, but instead we will go back to the traditional way. Having given you the physical ideas as to what is happening, I hope it is safe for me to go back and to introduce quantum mechanics as a set of postulates, which is what is usually done. So, I am going to introduce it as a set of 4 postulates. Okay, but then this can be confusing, because in some books you may find 5 postulates. Okay, this is because you see there is no standard set of postulates which have been introduced, but the 5 postulates in one book and 4 postulates in the other book, if you read the content, you will find that they are all the same. So, the number of postulates does not matter, the total amount of material which is in there is the one that is the same. And again you may wonder, why does one introduce this as a set of postulates? Well, you see, this as I always say, this is like joining religion. If you join a religion, Hinduism or Christianity, then there are certain things that you just have to believe, you do not question them, because there is no basic explanation for them. There are certain assumptions which you have to make, and once you make these assumptions, once you believe in certain things, you practice the religion. So, this is like it is exactly the same here. If you want to join the religion of quantum mechanics, you have to believe in these things, right. As I told you, I have made it physical by introducing the path integral approach, but these postulates that you are going to see, they will appear strange, and therefore, they are difficult to believe in, but it is not possible to derive this from anything else. If you want, you can assume path integral approach and derive many of these things, or you can assume these postulates and derive the path integral approach. So, the two are equivalent, right. But if you want to join the religion of quantum mechanics, you just have to believe in this. And you may ask, what is the big fun? Well, the fun is that once you have assumed this, you can make loads of predictions, and all your predictions are in complete agreement with the experiment, and therefore, that is proof enough. Anything that occurs in chemistry, you can explain, you can calculate using these postulates, and that is the justification for the postulates. So, I am going to introduce as a set of 4 postulates. Here is my first postulate. What it says, we have kind of introduced the idea of a wave function. So, what it says is that if I have any system in the morning or in my previous lectures, you see it is the electron that was my system, and to specify where the electron is, what was I doing? I was using the wave function. So, now we generalize and says, imagine you have any system, may not be just one electron, maybe 2 electrons or maybe 100 electrons, that is my system, okay, or maybe a helium atom has 3 particles, a nucleus and 2 electrons. So, to specify that system, or if I have a benzene molecule, that is my system, depending upon the situation, my system may be different, right. So, if you have any system, what is going to happen is that I will have a wave function which I will denote by this symbol is capital psi, notation is important, this is capital psi, and this psi is going to be a function of position x, y, z. Imagine I have just one electron, because we are thinking of the electron. I have one electron, and one electron, to specify this electron's position in space, I will need 3 coordinates, Cartesian coordinates. So, if the electron's position is specified by x, y, z. So, then in such a situation, what will happen is that the wave function will be a function of these 3 position coordinates. But not only that, as time passes, the wave function may change, and it may therefore depend upon time, it will depend upon time. So, therefore, you see, if we have an electron which is moving in 3 dimensional space, which is what it will do, then it will have a wave function psi, which will depend upon the position coordinates of the electron and the time t. Okay. So, I can illustrate this maybe how. Let us say I have just one particle constrained to move in one direction. Well, you may say that is artificial, but let me give you a very physical example. Imagine I have tungsten metal, this is tungsten metal, and imagine that I have a hydrogen atom bonded to the tungsten metal, which is a very physical thing. You can have hydrogen atom which is attached, chemically attached, strictly speaking, chemisorbed on the surface of tungsten. And imagine that I displace this hydrogen atom somehow and release it, I pull it to the side and release it, then I know that it will execute vibrations in the perpendicular direction. And imagine that I am interested only in that vibrational motion. So, then I say, okay, that is a one dimensional system. Why? Because I need only one coordinate to specify the position of the hydrogen atom. If I say, okay, I will be interested in other, it can vibrate in this direction also, right. If you displace it in that direction, it will execute vibrations, but I am not interested in that, I am only interested in this particular vibrational motion, and as long as I am interested in that vibrational motion, I can say this is a one dimensional system, because the position of the hydrogen atom can be specified by giving the value of the displacement of the hydrogen atom from its equilibrium position, that is enough. So, it is a one dimensional system. For such a one dimensional system, I mean, if I was interested in the vibrational motion parallel to the surface, of course, I will have to say that it is not a one dimensional system, but it will, I will need other coordinates like y and z perhaps, right. I will need y if I am interested in only this vibrational motion, but suppose I have this other vibrational motion perpendicular to the plane of the board, then I will need all the 3 coordinates. But to make things simple, I say okay, only this motion is of interest to me, and in such a situation what is going to happen is that I will have a wave function psi, and then it will depend, if you are interested only in this vibrational motion perpendicular to the surface, it will depend only upon position x, right. That is all, the wave function will depend only upon that, and then the time t. So, that is for a one dimensional system. On the other hand, if you had maybe, let us imagine this room, imagine it is completely empty. I mean, I want to make the system, my system as simple as possible, completely empty. Imagine it is a nice rectangular in shape, and I have one helium atom in this room. And what will the helium atom do? It will be moving around. Now, my helium atom, imagine it is just one particle, actually it is not just one particle, because there is a nucleus and 2 electrons, but I am interested in the motion of this helium atom as a whole, not I am not interested in how the electrons are moving, because I think of the helium atom as a single particle, correct. And then to specify the position of this single particle in space, I will need only 3 coordinates, right. I will have to worry about the internal structure later perhaps, but at the moment I am interested only in the motion of the system as a whole, and in such a situation what will happen, I will have my psi which is a function of, because I am thinking of helium atom as a particle, I would have psi which is a function of x, y and z, and then time. This is how it is going to be. On the other hand, suppose I am worried about the internal structure, how the electrons are moving around the nucleus, right. Suppose I can be interested in that. Then what is going to happen is, I will think of a coordinate system like this x, y, z, and I will say okay, my nucleus is at the origin, because I am not interested in the motion of this whole thing, I am interested in the motion of the 2 electrons with respect to the nucleus. Then what I will do is, I will have the nucleus and I will have one electron here perhaps and the other electron there. The first electron will be specified by its coordinates, which will be denoted by x1, y1, z1, and the second electron will be specified by its own coordinate x2, y2, z2. So, therefore, if I am interested in the motion of the 2 electrons around the nucleus, I will need 6 coordinates. So, I can say okay, this is a 6 dimensional system. Why? Because I need 6 coordinates to specify the positions of the 2 electrons in space, and the wave function will then depend upon what? Psi x1, y1, z1. I am lazy, I do not want to write the whole thing, but x1, y1, z1, x2, y2, z2, z2 finally, and then it depends upon time. So, this is how it is. So, depending upon the situation, you see your wave function will be a function of as many position coordinates as you need and the time. The number of position coordinates will depend upon what you think of as your system. But then you have the natural question, what is the use of the wave function? You are just saying okay, if you have a system, there is this function which we refer to as the wave function. Another word used for the same thing is state function, and in fact that is what is used here. The state of a system is specified as fully as is possible by the state function. Instead of using the writing state function, I could also write wave function, they mean the same thing. Okay. And then what is the use of this? That is mentioned in this part of the postulate 1. So, the postulate 1 actually continues. Okay. Well, let me illustrate this postulate with an example. Think of this hydrogen atom which is vibrating perpendicular to the surface like this. So, as I told you, the position of this hydrogen atom, to specify it you need only one coordinate if you are thinking of vibrational motion. So, this is that coordinate and I shall refer to that as x, and if the atom is not vibrating, you say what is going to happen is that I would expect it to be at the equilibrium position somewhere here, which I may denote as 0. 0 is the equilibrium position, and if it is moving, what will happen? It is moving away from 0 to that side or maybe to the other side. So, suppose I think of the wave function for this, the wave function for this will be psi, which is x, a function of x alone, only one position variable and the time t. So, what is the use of this function? The answer is that you think of a small interval along this axis. Remember our descriptions of earlier, wave function is going to give me probability, the information contained in the wave function is the probability. So, therefore, if we wanted to calculate the probability of finding the electron in this small tiny interval, in this interval, how much is the length of that interval? The length of that interval is dx. So, using the wave function you can actually calculate this probability. How will you calculate it? The answer is very simple. If you think of the probability physically, see, if this width of this interval is large, then you would expect that the probability also will be large. Well, if the width is small, the probability will be small. So, therefore, the probability definitely has to be proportional to that distance. So, if this interval is small, definitely I will have dx in my probability, because it has to be proportional, and our earlier discussions imply that it has to be proportional to square of psi, right. So, therefore, I would expect that the probability will be given by an expression which I shall write as psi of x t magnitude square. This is the probability, okay, according to this postulate. That is actually a postulate. This is the probability that the particle will be found in a small interval of length dx. Okay. Now, if you think of a helium atom in this room, we can generalize this very easily. If you think of a helium atom in this room and imagine that I have a rectangular, small rectangular parallelopiped region in this room, which I am going to draw on the board. Well, because we are thinking of the helium atom, remember the wave function is given by psi, which is a function of x, y, z, and this is helium atom. And for that, imagine in 3-dimensional space, okay, you have 3-dimensional space, you think of a small rectangular parallelopiped region in this room, and because it is small, I will say that the sides of this small volume are dx, dy and dz. So, this is going to be dx, the height is going to be dz, and the one of the sides, the other side is going to be dy. So, that the total volume contained in this rectangular parallelopiped obviously is dx into dy into dz. And it is obvious, I hope, that the probability that my helium atom will be found inside this rectangular parallelopiped, which is somewhere in this room, right, maybe here, a rectangular parallelopiped with sides dx, dy, dz. The probability that my helium atom will be in that inside that small volume has to be proportional to that volume. So, it has to be proportional to dx, dy, dz, and then naturally what would you expect? You would also expect psi x, y, z t magnitude square. So, this will be the probability that the helium atom will be within this room, sorry, not within this room, but within that small rectangular parallelopiped region. Now, in general, see what is going to happen is that this psi will be a complex number, it will not even be a real number, it will be a complex number with a real and an imaginary part, and that is why I had been putting this magnitude square, but instead of taking the magnitude and squaring it, if you like, you can also do the following. You take the wave function, take its complex conjugate, right, and multiply the two together, and that is nothing but the square of the magnitude of the wave function. So, instead of writing magnitude of psi square, you can as well write psi star psi. This object is nothing but psi star psi. Now, as I told you, depending upon the problem that I consider, for example, here I was thinking of a hydrogen atom, then you have dx, while if I am thinking of a helium atom in this room, what happens? This is my probability, right? This is my probability. Now, if you look at this expression, see there is dx, dy, dz, that is a volume, and you multiply that volume by this factor, you are going to get the probability density. Sorry, not the probability density, but probability. Take the volume, multiply it by this object, you are going to get the probability, and therefore, this object is referred to as the probability density. I mean, you take volume, I made a mistake, so it may not be clear. I take a volume and multiply it by density, I will get the mass. So, similarly, you take the volume, multiply it by this object, you are going to get the probability of finding it in that small volume. So, therefore, this object should be referred to as a probability density. So, psi star psi is a probability density. And what is usually done is, you see, your psi may depend upon several variables depending upon what your problem is. So, therefore, you do not normally write all the variables. So, you just say write psi, then multiply it by psi star, right, and if it is a helium atom, you will say okay, you will have to multiply it by dx, dy, dz to get the probability, while if it is just this hydrogen atom vibrating perpendicular to the surface, then you just have to multiply it by dx. So, depending upon the problem, you have to modify whether it is dx or dx into dy into dz and so on. So, we simply adopt a general notation. You say that the probability that the system may be in a volume d tau stands for dx if it is a simple one dimensional problem, while it will stand for dx into dy into dz if it is a three dimensional problem. So, therefore, this is going to be the probability. Psi star psi into d tau is going to be the probability, where what is d tau? D tau is written there, it is actually dx into dy, okay, dx into dy, it is not complete because you may have more things, there were dots there which seem to have disappeared. So, dx into dy into dz, if you have 10 variables there, it is a product of all of them. And so, again it is natural to refer to this as probability density. Now, I want to describe to you some very interesting consequences of this postulate. This is the first postulate in all its details. Let us take this one dimensional system, hydrogen atom perhaps vibrating perpendicular to the surface. In that case, the probability that the hydrogen atom is between x and x plus dx, let me be very clear. This is the point x, that is the point we are having position coordinate x plus dx, I am thinking of the probability that the particle is in this interval dx, and that may be obtained as psi star x psi x t into dx. This is the probability. Okay, that is what we have assumed, we have postulated now. But if that is the way it is, suppose I want to calculate the probability that the particle is anywhere between minus infinity and plus infinity. How will I calculate the total probability that it is somewhere between minus infinity and plus infinity? The answer is that I have to integrate this from minus infinity to plus infinity to get the total probability. But again, physically I know that if I calculated the total probability, as far as I am concerned, the particle is sure to be in that interval, because it cannot be anywhere else. So, the particle is sure to be in that interval, and therefore, if I calculated this, I know that it should be equal to unity. So, my state function or my wave function should be such that this integral must be equal to unity. So, this is a condition that my state function would have to satisfy, otherwise I am going to say that it is not acceptable. Because I am saying that I am postulating that psi star psi dx must be the probability that it is in a length small length dx. So, total probability has to be equal to 1. So, therefore, this integral has to be equal to 1. But suppose I have a function for which it is not equal to 1. For example, maybe I have a function, I can think of any simple function, but let me just take a function phi of x. I am not going to write the time dependence anyway, let us not worry about that. I want to just illustrate the point. Suppose it is such that phi star phi x multiplied by dx integrated from minus infinity to plus infinity, this will be an acceptable function if the answer is equal to 1. But suppose the answer is 10, and obviously this does not satisfy the condition that I want it to satisfy, correct. But then if you think about this, from phi, suppose I constructed phi divided by square root of 10, this is a new function, it is not phi, but a new function which I have constructed from phi. What have I done? I have multiplied it by 1 by square root of 10, and now this new function, if you took it, multiplied it by its own complex conjugate and the volume element dx and integrated from minus infinity to plus infinity, what will be the answer? The answer will be 1. So, even if my phi does not satisfy the normalization condition and hence is not an acceptable function, from phi I can construct a new function, right. I just multiply my phi by a number, and the new function is such that it is satisfying this condition. This process is referred to as normalization. And any function which satisfies this condition, we will say that it is normalized. Any function satisfying that condition is normalized, and if a function is not normalized, it is possible for you to normalize it. What do? You multiply it by an appropriate constant. So, suppose it is not 10, but if it is equal to a constant which I denote as a, then what will you do? You will multiply it by, you will take phi, multiply it by 1 by square root of a, that is all that you need to do. Then the new function is normalized. So, it appears as if I can if you have any function, it appears as if I can normalize it, right. Why? How can I normalize it? I take phi multiplied by phi star, integrate from minus infinity to plus infinity. I find whatever that answer is, take 1 by square root of that number and multiply phi with that, right. So, it seems that I can do this, it does not matter what the function is, but that is not true, because Suppose it so happens that this number, when I did the integral, the number turns out to be infinity, right. I mean, I can, if you want, I can give you examples for this. A function like e to the power of, suppose the function is e to the power of x by 2. Well, I do not think I will work this out, but if you actually perform the integral, you will find that phi star phi integrated from minus infinity to plus infinity actually is infinity. So, if it so happens that if a is infinity, then what will you do? You will take your phi multiplied by 1 by square root of a, but a itself is infinity. So, 1 by square root of a will be square root of a itself will be infinity, and therefore 1 by that is going to be 0. So, your new normalized function is 0, which is totally meaningless, because you cannot say that I have a particle and its wave function is identically equal to 0, because if the wave function is equal to 0, then the probability of finding the particle anywhere in space is 0, but I know that the particle is there. So, therefore, you see, a wave function equal to 0 is something that I do not want, that is not acceptable for me. So, therefore, the condition is that this a has to be less than infinity. If a is less than infinity, then I can normalize the function, and a function which satisfies this condition, that its integral actually phi star phi is less than infinity, is referred to as a square integrable function. The word is itself obvious. You take the square of the function, roughly speaking, integrate it from minus infinity to plus infinity. If the answer is less than infinity, then you say that it is a function that is square integrable, right. The word square integrable means this integral equal to a is less than infinity. So, you can carry out this process of normalization only if the function is square integrable. Only if a is less than infinity can you carry out the process of normalization. So, we therefore, what we will do is we will not impose this condition. It is not really necessary to impose this condition. It is enough if I impose the condition that the function is square integrable, because as long as the function is square integrable, I can carry out the process of normalization and get a wave function which is satisfying that condition. Okay. So, that is one result, and another result that I would like to speak about is the following. Suppose I say I have a function phi of x, and I am going to say that it is of the form sine inverse of x. Well, of course, I mean you will have to say x is between 0 and well minus 1 and plus 1. This is only for the sake of illustration essentially. So, if you think of this interval running from minus 1 to plus 1, imagine I am evaluating this is x running from minus 1 to plus 1. Suppose I put x is equal to 0, then what will happen is that I will have sine inverse of 0 as my wave function. Now, sine inverse of 0, it has a problem. What is the problem? Sine inverse of 0, one possible answer is 0 itself, right, but there are other possible answers. It may be pi, sine inverse of 0 may be pi, or it may be 2 pi, it may be 3 pi, it may be 4 pi, all these are possible answers. So, therefore, this is a function, sine inverse of x is not a single valued function, it has multiple values at the same location, at the same point it has a large number of, in fact infinite number of values. So, suppose your state function happen to be a multiple valued function, then you are going to run into problems. What is the problem? See, suppose I want to calculate the probability density at this point x is equal to 0, then what I will have to do is I will have to take sine inverse of 0, take its magnitude and square it, right. Now, which value am I going to take here? Would I take the value 0 or would I take the value pi or would I take the value 2 pi and so on, right? That is not clear. So, therefore, we do not want such a problem. We know that probability density is a number which has to be unique. It is something which is physically meaningful, which I can perhaps measure. So, I want only one value for probability density, I do not want multiple values. And therefore, what should I do? I will have to impose the condition that my state function is a single valued function. I do not want it to be a multiple valued function, because that is going to give me problems. So, at any point it can have only one value, not more than one value, only one value. So, therefore, I say that my state function has to be a single valued function. Now, suppose I have a function phi of x, which I will write. I mean, this may appear a little bit complicated, but if you think about it, it is a nice example. I want you to think of this function. I know it is a, I mean, for some people it can be a difficult function, but this is an example, nice example for a function which has a peculiar behavior. Now, if you look at this function, you have e to the power of minus x square. So, as x becomes large, definitely what will it do? It will decrease the function to 0. So, therefore, I know that here the function is going to be vanishing, on the other side also the function is going to be vanishing, but the behavior in between is what is very interesting. Okay, this is x is equal to 0. So, suppose you are somewhere here very close to x is equal to 0, but on the right side of x is equal to 0. It means the value of x is very small, maybe let us say I think of this point which is at 0.01. So, this x is going to be 0.01, that means I am going to have e to the power of 100 here, correct. Here I am going to have e to the power of 100, e to the power of 100 plus 1, it is e to the power of 100 itself, because it is such a huge number, and if x is very close to 0, this is almost 0. So, the e to the power of that will be 1. So, you will have 1 by e to the power of 100, which is extremely small. So, as you are approaching s is equal to 0, from this side what will happen? The function actually decreases and it approaches 0, right. That is what happens with this function. As you approach x is equal to 0 from above, okay, the function far away, of course, the function is 0, but as you approach, the function actually increases, but very close to x is equal to 0, the function has a value 0, as we have seen. So, therefore, it should turn around and it should approach 0 like this, correct. Now, suppose you think of x very close to 0, but on the negative side. So, here you are going to have, let us say, minus 0.01, right, a point where the value of x is minus 0.01. What will happen? You will have x equal to minus 0.01. So, you are going to have e to the power of minus 100 there. So, e to the power of minus 100 plus 1, e to the power of minus 100 is almost 0. So, therefore, this 1 you cannot neglect. So, you will have 1, and in the numerator you see x is very small. So, e to the power of minus x square is almost 1. So, you will have 1 divided by 1 plus e to the power of minus 100, and how much is that? It is 1. So, as you approach x is equal to 0 from the negative side, what happens? The function actually behaves like this. It approaches unity if you are approaching from the negative side, while it approaches 0 if you are approaching from the positive side, right. Now, this is a function that is very interesting, because what it does is, when you cross the point x is equal to 0, the value of the function jumps, it jumps from 1 to 0. See, if you are going in this direction, the value of the function steadily increases until it reaches the value 1, very close to x is equal to 0, and as you cross x is equal to 0, the value of the function suddenly jumps, and therefore this is the behavior of the function. It suddenly jumps and then it does this. So, you say that this function is a function which is discontinuous, it has a sudden discontinuous behavior at x is equal to 0, right. Now, suppose I say that this is my wave function, this function is my wave function, then what it means is that the probability also, probability of finding the particle will also change discontinuously, and usually there is no physical reason for that to happen, right, unless you have some peculiar situation and so on. In fact, there is no peculiar physical situation which will make the probability change in a discontinuous fashion. Probability always has to vary smoothly and continuously in all physical problems that I know of. So, therefore, what is the way out? You cannot have such a function in which the probability will change in a discontinuous fashion is not acceptable, and therefore, what will we do? We will say that my wave function has to be, or our wave function has to be varying smoothly and continuously, it cannot be a discontinuous function. So, the wave function, it has to satisfy two conditions actually. One, it has to be square integrable, and the second is that it has to be a continuous function there are three conditions, not two. Third being, it has to be single valued, at any point it can have only one value. So, these three conditions have to be satisfied by any wave function which is acceptable. If these conditions are not satisfied, then I will say that my wave function is not acceptable and I am not going to take such a wave function. These are all physically motivated requirements, right. So, if I have some equation which I will have later, like the Schrodinger equation, which you solve and find your wave function, and if you get a solution which does not satisfy any of these conditions, then you will say, okay, that is not something that is acceptable, and simply throw out that function. Thank you for listening.